You know, boss, it all comes down to this, doesn't it? Hi, I'm Keith Mauney, chairman and founder of the KMA Training Theater, and I'd like to introduce you to the fellow that I work for here. Though he's a product of the Walt Disney Company, it was this little statuette that actually got this videotape series that you see right here tonight started. Everything that flows forth from the KMA Training Theater, or Keith Mauney and Associates as the company is properly called, was inspired by the conviction and the commitment of one man, and that's Walt Disney, who brought to the entertainment industry, of course, a whole new level or a whole new standard of the way that adult and family entertainment would be conducted. It was that inspiration from that one man, and more importantly from this intangible entity, that has led to the recreation of adult education as expressed here most recently in the KMA Training Theater. This sort of slightly off-center style is more than just a style to entertain you. It is a firm and lifelong commitment brought to you by all of us, the cast members of the KMA Training Theater, to the classroom in an attempt to bring forth the most credible, practical, clinically reproducible, and effective informational interchange that we possibly know how to do. Of course, cast in light of what the boss would be most proud of. With that in mind, I hope that you enjoy this expression of our educational and informational and entertainment output. It is certainly something that we are committed to in a lifelong fashion. Now, having joined us here on stage tonight at the KMA Training Theater, you now become part of the international cast that is ever widening, I'm pleased to say, and it's always checking in. So, once you get through and once you step past the curtain behind me, which will rise very, very shortly, and our production will soon begin, then you'll become a part of the ever-growing and international experience, which has been known simply as KMA. We're glad to have you with us tonight. I hope you enjoy the show. Hi, and welcome to KMA's Statistics for the Non-Statistician. Ladies and gentlemen, in just a moment it will be showtime, but let me tell you, I have been living for this presentation on tonight's stage for a long, long time. And we're going to show you statistics in a way that is not only fun, as I hope you would expect from the crew around here, but in a very instructive and engaging sort of way. Not because it's me doing it, but because the subject can really be fun if we do it just right. And believe me, you're going to see that's the case before we get through. Don't like statistics? Let me tell you about my first exposure to it. We had out one of those big sheets of easel pad paper taped to 3 other sheets of easel pad paper back in 1978, doing our first statistical correlation series with angiography, and the project took 2.5 years, and we still never did get finished with it. Nowadays, there are wonderful, easy-to-use software programs that will get you through the entire process safely. But you know, the problem with that is that the computer does your number crunching and therefore your thinking for you. So that's why I'm here tonight to share with you how easy it is for the basic sorts of statistics that we work with here. It will serve to open the door just a little bit, I hope, to the science of statistics, give you a little better feel for how misleading they can be, how easy it is to misuse them to create your own support for your own points, and how to watch out when somebody starts throwing numbers at you, and how to applaud when, in fact, numbers do pass the litmus test for credibility. It's the language of scientists, and that's what you and I are, so let us begin. But oh, sit tight. You'll want a bowl of popcorn and some candy and a soft drink or tomato juice for this one, because you're going to enjoy it, I hope. Let us begin. Statistics was born in ancient Greece, I contend. I would trace it all the way back to Pythagoras, who, among other Greeks of his time in the ancient years, took a plumb, that is a string, tied around to a rock, and held it up to the horizon there on the ocean. And let's face it, there's a lot of shoreline in Greece. By studying the relationship of the perpendicular angle of the gravitational pull against the rock to the horizontal distribution of water out on the ocean surface. Pythagoras, at least, or others like him, Pythagoras for us was first to create the geometric model of a right triangle. And surely, working in sand, as you see here on the graphic, by playing with the various positions of a series of right triangles, he discovered that it would make an actual square, or a square with a hollow point within. From this, bottom line was, he determined the mathematical relationships that exist for a right angled object, a right-angled triangle. From this, of course, the Pythagorean theorem was born, but Pythagoras was much more than just describing the relationship of a hypotenuse and a right triangle to the other two sides. He was actually one of the principal contributors to the statistical method of analysis, describing the world in which we live using numbers. You and I use numbers every day, and in science and in economics, of course, we always use statistics, and there's no way to divorce ourselves from it. So let us get a better appreciation for how it all begins to work. It's been around for a very, very long time, obviously, as you can see implicit by this, and it's going to be around a lot longer than you and me, so let's go ahead and have our piece of the rock. One of my favorite inventors would be Dan Jones, who invented a lightning detector a number of years ago. Now, Mr. Jones got inspired there up in Boulder, Colorado back in 1984. But being an innovative inventor of sorts and recognizing the need to come up with a better sort of interventive device to prevent the electrocution from lightning strikes by golfers and swimmers and others just out working outdoors throughout the course of a year here in just this country alone, invented a lightning detector. Now, in Florida, where Jones lives, more lightning strikes occur there than anywhere else on the North American continent and perhaps in the world. But Florida certainly is the lightning capital of the United States. Testing it out there in Florida, he discovered that, and here I will quote, testing it out, he described his invention. Let me read for you. Jones's device is triggered by an electric field produced by an electric charge generated inside storm clouds. Okay, well, by that so far. Draws a weak current from the sharpened tip of the antenna, getting rather scientific, as you might expect to hear from the dais at a scientific meeting here. The weak electric current is utilized by the electronic circuit to sound the alarm. We're getting over into engineering science now. And the bigger the current, the more frequently it beeps. Well, that would make sense to a simpleton like me. The bigger the current, the more it beeps. The more frequently it beeps is an indication of a higher probability of lightning. I see. Well, I need to buy one of these. You need to buy one of these. And the whole, we could get in on futures here with lightning probability detectors on the ground floor. And ladies and gentlemen, there'll be a phone call, an 800 number for you to phone as soon as we're over, where you can go buy your own. Oh, I'm sorry. We'd better just find out exactly what the true nature or the validity of the usefulness of this product is before we send in our checks. The device forecasts lightning by detecting the electric field. The device, listen closely, the device will not predict where lightning will strike, but only will detect the high probability of a strike. And couldn't you do that by sticking your head out the window and looking in the sky and seeing the lightning clouds around? Well, certainly you could, but is it possible to more closely, more accurately predict the likelihood, the statistical likelihood of a strike? Well, if I'm standing out there in a field with nowhere to run to except the one big tree in the middle of the field and am drawn to it, then I would certainly want to know whether or not there's a likelihood of lightning striking close by or no. So numbers don't always answer all of our problems, do they? It's not like the government taking care of all of our problems, is it? That's the last thing we want, I think. It's simply trying to get closer to an answer. And let's find out exactly how that occurs. We are going to use, in most of the ultrasonic circles, statistical measures of sensitivity and specificity. This has certainly been a problematic topic since I was first exposed to it back in the 1970s for us as clinicians involved in working in the field of science. Sensitivity, specificity, positive predictive value, PPV, NPV, things like that, accuracy. Well, where do these all fit? Well, sit tight because we're going to lay them down and we're going to have a good time with it. I can't wait. If I'm talking too fast, play me back at 1/2 speed because I'm getting excited. Sensitivity is classically defined as the percentage of subjects with a given condition that we are testing for that tested positive for it. Let's say, for example, that we are testing for, a head cold, and we want to bring a room full of, well, let's go out into the waiting room and test everyone for a head cold. And we'll determine that they've got a head cold by asking them. And we'll test them for a head cold by just looking at them. If they got a big old swollen red runny nose and got a tissue up there blowing it, then we'll figure they got a head cold. And then we'll ask them if they've got a head cold after we test them for it. Sensitivity would be our percentage of subjects that had a head cold that we in fact, before we asked them, that we in fact determined had a head cold. We were testing them to see if they had a head cold. We used a pretty good test. And what percentage of those subjects that actually had a head cold did we actually detect? There's a better example that's forthcoming, but it's on its way. Sensitivity is easily differentiated from specificity for me by simply remembering, in fact, this is the only way I can do it, is just remembering that we must be sensitive to the patient who is ill or the patient who has disease. If we are using sensitivity and specificity in clinical terms and we're using these measures to test for a disease condition, remember that we must be sensitive to that patient who had the disease because they were probably uncomfortable, a little irritated, or something of that sort. Didn't really want to be there as part of our involvement. So sensitivity refers to our need to be sensitive to the patient with disease. That's the only connection it has to statistics or epidemiology or anything else. But at least if nothing else, it helps you remember it. And of course, specificity is the other thing that wasn't sensitivity. There are only two, and you memorized one, and you knew that there were two and what the other one was, then you know what the other one refers to. Specificity must refer to the percentage of patients without the condition, without the disease, that we tested negative for it. In other words, we said, you don't have a head cold, do you? And they come back and say, well no, I don't. So the percentage of those that we said, you don't have a head cold, that really did not have a head cold, would be an indication of the test's specificity. Isn't this fun? Oh, it only gets better. Now, what we want to do is figure out exactly what percentage had disease, which percentage did not, and that sort of thing. What we'll end up doing is drawing what they call a chi-square diagram. Chi just means 4. You mean a 4-box diagram? Uh-huh. That's it. And of course, we refer back to we give deference to the ancient Greeks who made it possible for us to have this visit here on the stage this evening at the KMA Training Theater and talk about this subject. So we'll refer back to the Greek letter chi. It's just a 4-square box. And what we're going to do is put all of our findings, all of our test findings, and all of our known conditions, we'll just put all of our patients into 4 little piles. And that's all we're going to do is just shove them over into 4 little piles, but it looks neater with a box, doesn't it? You can draw this box any way you want. That is, you can draw it so that the elements across the top run down the side, and the elements that are running down the side in my box run across the top. You can draw them backwards and forwards any way you want, as long as you understand what's in the box. People that memorize how to draw the box drive me crazy because they recognize a facsimile. And that's all they recognize is a facsimile. You remember the person in college? I remember her now, but I can't think of her name. But she could memorize everything, every chapter in a textbook, and complained when she got a 97 on the exam. I was lucky to get a 77 on the exam, and I was working long into the... People can just memorize. Just show me once and I'll know it. Will you really know it? There are some people that really will. I think she was one of them, too. And some people can just memorize things, regurgitate it, and never really know what it truly means. It's those people that truly know what it means that I want to associate with. It's what I've dedicated the rest of my life to. It's what we started here as the KMA Cast, a lifelong project with, is to spread the word so that we all know what it is that we're doing and why. And then we'll have more meaningful conversations in the bars and across the dinner table and at the street corners as well. Here we go. What we want to do is arrange our data into 4 separate piles. That's it. Now, let's not get too busy here. Let's first separate them into 2 kinds of piles. Let's just look at it. Let's consider reality first. Forget the fact that we're going to test them. Let's consider reality. What we want to know is, did the condition really and truly exist? The condition that we want to test, did it really truly exist or not? I mean, it either did or it didn't. We have to make a stand here. It was either present or it wasn't. If I was going to test for whether it is night or it is day, I guess that I would have to decide whether it is night or whether it is day. And one good way of doing that would be to look at a clock or ask somebody, ask a rooster if he's already crowed or not, or go out and look and see if the sun's up, which wouldn't work up there in the North or South Poles necessarily, would it? Oh, more on the limits of statistics before we get through. But we have to decide whether the condition existed or not. And we'll divide our piles into 2 separate categories. Those that had the condition and those that did not. And we put them on 2 sides. They put them on across the top and bottom. I put them from left and right. On this, the true patient condition, that is the condition. Now, I'm considering the true patient condition to be disease. We're kind of clinical today. In this evening's visit, we're talking about was the disease condition present or not. Well, if it was present, I'm just going to, by convention, because, hey, the slide's already got it there,
I'm going to put those on the left-hand pile, and I'm going to put those that didn't have disease over on the right-hand pile. Now, I've got them separated into two separate piles, left and right. Then I'm going to go in there and I'm going to test them. I'm going to test them. Ideally, I'm going to test them not knowing whether the condition is present or no. But I'm going to test them, and I'm going to put all my positive tests in a top pile, and I'm going to put all my negative tests in a bottom pile. And then I'm going to go back and visit with my piles, and I'm going to compare out of my positive tests who now really had disease. And out of my positive tests, who really didn't have disease. Then I'm going to go down there and look at my other set of piles, and I'm going to find out in my piles that said that, well, I didn't find any disease with my test. I'm going to find out, okay, out of all those that I said didn't have disease, which ones truly did not have disease, and which ones truly did have disease. And you know, once you recognize which ones tested positive and negative, and which ones had it and which ones didn't, then running the numbers is ridiculously simple. The only problem with these test questions we run into on certification exams sometimes is, and the problem with this when we try and do it in our own facility, is trying to figure out your piles. If you've got piles, how are you going to deal with them? And it's really very simple. Start easy, work more complex. It never gets more than 4 piles. You will never have, at least not in statistics like this, you'll never have more than 4 piles at once. And that's a pretty comforting thought, isn't it? What I'm going to do is simply cross-reference my piles. In one corner, I'm going to put everybody that had disease, that I tested for disease and found it to be present. And I'm going to, well, you get the idea. Everybody goes into 4 separate corners, and those are my piles, organized piles, as a matter of fact. I'm going to total up all my all the patients and all the subjects in the series right there, how they all broke out, but that's coming up in just a minute, so sit tight. I'm sorry, if I start to sound like Andy Griffith, it's because I come from North Carolina anyway, and the Andy Griffith approach to statistics has been long overdue, I think. To that end, ladies and gentlemen, let me introduce our study that's going to take you and me tonight through statistical analysis, and we'll have a good time doing it, I hope. To do so, I'm going to need some eggs. Did you ever buy eggs lately? You know, I had an egg sandwich. I'll go ahead and break down in a minute. I had an egg sandwich for breakfast today. Actually, I had 2 egg sandwiches for breakfast today, but they were egg beaters, and they weren't anywhere near as good as the original equipment that you see right here. Nature's perfect container, an egg. How would you describe an egg statistically? Well, how would you describe an egg? The egg that you see right there, how would you describe statistically? Well, it's longer on one end than it is the other. I guess you could do a long axis, short axis ratio, couldn't you? You know, you do pretty much the same thing with head circumference there in OB ultrasound, don't you? You do the same sort of thing with measuring the percent diameter stenosis in vessels using ratios there in Doppler ultrasound in vascular disease. Oh, wow! I'm getting ahead of myself and you use statistics all over the place, don't you? You have to, the problem comes when you decide how you're going to generate your piles. And those statistics often generates piles, if you catch my drift. It's real easy to deal with these piles when you know the technique. Your data isn't always straightforward, isn't it? Sometimes it may approach you at a different sort of angle. Is this the same egg as you saw in the preceding frame? Well, yes it is. Doesn't it look a little different? Yes, it does. So statistics is very, very helpful to eliminate the subjective assessment, the operator bias that we may have in trying to differentiate the characteristics of something as simple and silly as an old common chicken egg. Now, here's another egg, and you pay more for these eggs. I know because I just bought some not too long ago. Are they any better than the white eggs? Well, you know, eggs come in all sizes and all kinds of shapes and all kinds of prices, don't they? You go into the egg department there at the store, there's a whole wall of eggs. You got some double A's, you got some double A jumbos, you got double A large, single A large, you got small and medium, and you know they're all out there, but you just go in there and you flip open the lid and you find some that aren't broken, you take them home. Oh, no. Ma'am, sir, you're spending money the wrong way. Stick with me and I'm going to save you some bucks and return for you the cost of investment in this videotape series tonight. Sir or madam, you'll never buy eggs the same way before you get through. Take a look at this egg. Is that a jumbo? Is that a double A? Is it large? Is this magnified? You know, a computer back in the broadcast studios here at the KMA Training Theater, we can do anything to that egg you can think of and alter your perception by altering what you see. It's easy to have a digitally manipulated egg, you know. Can't do that in the store, but you're trusting, well, I buy AA large. Oh, do you? Well, are you paying too much for them? Should you be buying single A medium and end up with a better egg value? Times are tight. Money is money. Don't spend a dime you don't have to. Let us continue. What about this egg? Kind of short and squatty. I'll tell you, that one's a medium. That's not a small. Mr. Mauney does not buy small eggs. He doesn't buy jumbo either. Not anymore, and I'm here to tell you that you shouldn't either. Let's take a look and see what's going on right here. If you want to go select eggs, you go walk over to the store's egg department, and you say, excuse me, I'd like some eggs. Well, go grab some. Go buy whatever you want. You flip open the lid. Whoa! There's an outlier right here. They're all white except for that brown one, and of course the clerk ought to be flipping the lid open because you're going to pay extra for that brown egg. It is easy to spot an abnormal finding, so to speak, when the other 11 eggs should have been brown too. I was paying for a dozen brown, but I got 11 white. Something's not right. It's easy to spot the data difference right there when the data is significantly, substantially different from each other. But statistics has, at its finest hour and contribution, the ability to differentiate subtle abnormalities there in normal and abnormal conditions. And this is why we use statistics so often, because if we get a good statistical result, then our test that differentiates normal from abnormal, aha, is very, very good. And then you're cooking eggs with gas. So what's wrong here? You got too many white or too few white eggs? Well, I don't know. It depends on what kind of condition you want to test. If I want to test whether it's a brown egg or a white egg, all I got to do is flip open the box. Provided, of course, and you must take this into account, that the lights are on in the grocery store. I didn't break in at 3 o'clock in the morning down at the corner egg store and just try and conduct my experiment because I'm too cheap to buy them. They don't give us a whole lot of money for things here. So we had to come up with our own statistical analysis experiment to figure out what's going on with eggs. And I got pretty concerned about this because there are too many eggs out there and not enough standards. There's not a table for... You get the nutritional ingredients there posted on the wall at the fast food restaurants. How come they don't tell us how they figure out eggs? So I got on the phone for you, ladies and gentlemen, got on the phone to the National Egg Institute and said, look, folks, how is it that you describe... Hello, and had someone else call back and got the criteria for differentiating eggs, grade A, grade AA, small, medium, and there are actual statistical criteria for this. And you need to double-check this yourself. We're going to present our data in just a few moments. To that end, I'm going to need a population of eggs, and we're going to go down to the local Tom Thumb Page Food and Drug Store, because that's where egg prices were on sale this last week before we shot this. And I'm going to bring in just a little bit later time, my friend, the old Wishnick troll from the 1960s. You may have seen these as good luck trolls here later on in the 80s and in the 90s. But mine goes back, well, never mind how far mine goes back to, but that's an original one. These three players together are going to step up center stage and teach us everything we really need to know tonight about statistical analysis. Let us begin. The National Egg Institute says that, well, in order to determine whether the egg is small, medium, or large, grade A or AA, or not A at all, then we take a look at that egg dropped onto a piece of marble from a slight height of several inches, and take a look at the area of egg yolk ratioed, I'm saying egg white. Now, I never was very good at reading graph paper, and we figured that probably wasn't an easy way to test the accuracy or the utility of ultrasound in determining the quality or the value, the validity of egg measurements. The other thing that the Egg Institute told us was that we measure the yolk height. And yolk height is the predominant criterion that goes into selection of egg size. The larger the egg category, the higher the yolk height will be. And generally speaking, the higher the yolk height, the larger its cross-section surface area will be. To keep this test simple, because that's all we could handle around here, was we would measure yolk height. We got out the old yardstick because, you know, it costs electricity to turn that ultrasound machine on, and, well, the boss wouldn't let us spend a whole heck of... He's kind of goofy anyway, so he wouldn't let us spend a whole lot of money with this anyhow, so we tried the old meter stick, and kind of hard to tell. Not as precise as ultrasound because, you know, the actual resolution on a high-resolution imaging system is about 0.25 millimeters. So, hey, are the egg producers using ultrasound to measure yolk height? Shouldn't you take your system down to the... You need to get your eggs at home tonight and break them out and test them according to my table right here. What we did was drop those eggs there into, very gently, we cracked them under water and dropped them into a tray of water. and then scanned the egg yolk from a probe immersed gently in the surface. We backed off the image transducer to the optimal focal zone. The natural transducers have a natural focal zone and, of course, a dynamic focal zone wherein focusing is optimal. We determined what that was for this manufacturer's brand of transducer instrumentation and measured vertical height from leading edge to leading edge, of course, the leading edge of the egg yolk itself down to the top, the leading edge of the tray. It was a plastic tray. We couldn't afford a marble tray, and again, because we're too cheap, we measured the yolk height. That's all we did. So what you're looking at is an egg yolk. What you're looking at, interestingly, is an experiment in acoustic physics that shows that the leading edge of the egg yolk is acoustically brighter than the interior contents of the egg yolk till you get down to the dead center core. And the reason for that halo around the outer part of the yolk is the interface difference between water and the egg yolk. But this is not a discourse on physics. It's just simply saying that's the leading edge of the egg yolk. So we measured these things at 1.2 atmospheric pressures and a standard room temperature because we didn't like getting very hot. We had the air conditioning on to the point where we were very, very cool, and things on which this was measured was completely level. And we controlled all variables under our control. Now, the study was a single-blind study because once I took the egg out of the box and cracked it under water, I wasn't sure whether it was grade A, double A, large or small. So we did kind of cheat. It wasn't a double-blind study in which we would have someone hand us an egg from a dark basket. We were afraid we'd probably reach in there and grab one and break it, and then we'd have to go buy some more eggs. But we were too cheap to do that, so here we go. And you need these explanations for whenever you do this. Ladies and gentlemen, our egg-sperimental population broke out like this. And anyone that shows you their results must first show you their experiment. Don't show me your numbers. And I'm being very serious for a moment here. Don't show me your numbers. I want to see your experiment. And I want to see every single piece of data that went into it. You ought to be asking me, where are the other eggs? Where are the other eggs? I got a dozen double A large. Actually, I bought 5 dozen eggs. That was all I could afford. I had a coupon, buy 2 dozen, get a dozen free, and then I sprung out of my own pocket for the other 2 dozen. But I did distribute my egg population, my known disease distribution population, so to speak, my known condition population over a wide range of conditions. What we're going to do is use ultrasound to test for whether or not that is truly what we'll consider a big egg or not a big egg. And we need a large number of big eggs, and we need a large number of small or not big eggs too. And we must decide at what point we're going to make the call based on ultrasound measurement, a big egg or a small egg, because the Egg Institute would not tell me that over the phone. What I had was 54 eggs out of 5 dozen. And you've got to ask, where are the other 6? We'll get to that a little later on. But in your statistical analysis, you must account for every single subject that came through your door, through your care, and you can't just say, well, we couldn't do 15 cases like that. We're going to throw them out of the study. Oh, no, you can't do that. But we did, and that's okay because everybody else seems to as well, don't they? Because otherwise we won't have a story to tell you tonight. So remember that this, well, tongue-in-cheek to begin with, but remember that in true statistical analysis, you have to take into account and take a stand on every single case you did and account for every single shred of data that went into that entire experiment, not just report your results. What we did was read the box. And we said that if the box suggested it was a big egg, they called it a big egg, large or jumbo, we'd call it a big egg. Medium small was a small or medium egg. That was not a big egg. So the box either said it was a big egg or it was not a big egg. One of the two, and I put my data into 2 separate piles, big eggs and not big eggs. Now I tested them randomly, but the outcome of my statistical analysis was, are you a big egg or are you not a big egg? And then I did my test. I measured the yolk height, and using criteria that we will talk about in just a moment, I determined whether or not, using ultrasound now, my finding was a big egg or not a big egg. And then I compared my finding, of course, to whether the box said it was a big egg or not. And you see how simple it is? That was the whole study. That's all you've got to do to compare your results to angiography, compare your results to epidemiology, compare your results to anything else. Compare your results to the patient's payment history, compare your results to any the barometric pressure, the tire tread wear on the spare tire in their trunk, whatever you want to compare to, this is how you can do it. Now, in our statistical experimental population, what we had right here to test was a true condition, that true condition being, are you a big egg or are you not? My test will answer that question. my reading of the box that that egg came in will answer the question, and I am assuming that the box never lies to me. If the box says that it's jumbo or large, that it really is a big egg. If the box says it's not a big egg because of some other marketing hype, then it is really not a big egg. And then I'm going to use my test criteria and then divide my patient tests into two piles, compare those two piles to the two piles that I had for the reading the box, and I am set. Now, you'll see around the edges at the right-hand side and down across the bottom the tally of our numbers of tests we did, and that's going to be helpful for us in just a few minutes, as you'll see. I got to have some criteria. What constitutes a big egg or not? I could go look it up in some luminary's textbook and say, I'm going to use their numbers. But that would be like the guy in the clock shop who set his clocks based on the whistle that blew at the factory down the street every day. The whistle would blow at 5 o'clock every day. And the clockmaker would set his clocks that sat in the window right there to the whistle. One day, while standing out in front of his clock on the way to work, a gentleman stopped by and said, "Good morning, how are you?" And he said, "Oh, I'm just fine, thanks. How's business?" "Oh, kind of slow this morning. Ought to pick up a little bit later on." And he stopped and set his watch. And he said, "Well, say, where are you headed off to?" And he said, "Well, I work down there at the factory." And they talked for a little bit, and it was determined that the fellow who stopped to set his watch there at the clockmaker's shop was a fellow who blew the whistle down there at the plant every day at 5 o'clock. And he said, well, you blow the whistle? Said, "Yes, sir, I just want to stop and check my watch against final time watch." They might have been calibrated to each other, but they could have been off by 4 or 5 hours for all that matters. So what we need to do is to determine our own criteria, our working criteria, for whether or not we've got a big egg or no. So what we did was make 54, as I recall, 54 egg measurements right there, and simply chose what looked like the best differentiating point between large and small egg yolks. That's all we did. Now, I could have made my Gaussian curve right here anywhere I wanted to. I could have set the measurement of yolk height anywhere this is the horror of statistics. I can do whatever I want. And believe me, I picked a number that gave me the best outcome for you so that I look good here on camera tonight. What I decided was, after looking at all the eggs and then finally asking 3 people walking down the hall to give me a number between 1 and 10, and the first one said 2, the second one said 8, the third one said 7, that's it. I'll use 2.87 as my yolk height to determine whether it's a big one or a small one. That was it. And everything above the big egg, everything below that was a small egg. And then from there, just to make sure I give you plenty of numbers, I'm going to tell you that the average yolk height of the not a big egg was 2.74 centimeters for the medium egg population and 2.81 for the large. However, the extra large eggs had a somewhat significant difference, that coming in at 2.94 versus 2.93 for jumbo. The only relevant thing from this whole series for you in terms of the seriousness of the study is that jumbo eggs are overpriced. You're paying $2, and the extra large eggs are only slightly larger than the large eggs. If you want a big egg on your egg sandwich there in the morning, then I would recommend that you buy extra large instead of medium or large. They only cost a few more pennies, but you're throwing money down a rat hole if you're buying jumbo based on my criteria here. So, let's just see how the numbers fit out. What I want to do is divide my piles up. I'm going to have 2 big eggs and not big eggs, and that division is going to be based on reading the box. Now, you can go ahead and set up your box with the tests you did if you want to. I certainly don't care. What am I going to do? Jump out of the TV set and go, naughty boy, naughty girl? No. What we want to do is set up the box any way that you want. As long as we set up the box so the numbers distribute properly, we're in good shape. The box said it was a big egg. And we had 21 total big eggs. That would be extra large or jumbo. So I had 21 in that population. Now the box said, this is not a big egg, you cheapskate. Big egg, jumbo, jump by jumbo, your best buy. Yeah, I'll bet. The box said not a big egg 33 times. That is, I had 33 eggs that were not big eggs. Now some of them were cracked, and we'll account for the ones that we could not get into this series before we get through. So I had a pretty good number of big eggs and not big eggs to give my ultrasound test a good run for the money. I'm pretending that I don't know they're big eggs or not big eggs. That would be a single blind study, obviously, wouldn't it? Now, the results of my test came in as follows. Forget whether they were big or little eggs for a moment. I found 18 big eggs by my criteria that I just shared earlier. By my criteria, there were 18 big eggs that, as it turned out, were in fact big eggs. I said it was a big egg. I went there and looked at the little code number on the egg, which I'd written down myself, so I already knew anyway. And I said, you're a big egg. But hey, I'm an accurate kind of guy. I got no axe to grind. I got 18 right. I said there was a big egg, and the box said there was a big egg 18 times. Now, there were 21 big eggs, and I picked out 18 of them. Can you tell that? Reading straight down, there were 21 big eggs, and my test happened to pick out 18 of them. Aha. All right, smarty. Well, just tell me this. When you had a big egg in the box, how often did you say it was a little egg? Oh, that was 3 times. I missed 3. I missed 3 times calling a big egg. I said it was not a big egg, and as it turned out, it was a big egg. So I guess I undercalled that one, didn't I? By my criteria, it just did not fit. So by my criteria, it said that it was not a big egg. Now, that could be a fault with my technology, my measurement technology, or it could be a fault with my selection criteria for not being a big egg. But the point is, I said it was not a big egg, and the box said it was. And I always believe the box. The box is my so-called gold standard, gold being an immutable substance, one that does not react very easily with other elements there in the periodic table. Well, the box said it was not a big egg in 33 cases. So I had 33 chances at picking out not big eggs. In 7 of those not big eggs, my test said, well, look, by my criteria, it is a big egg. So I've got to call it that. And I missed those. I said it was a big egg. The box said, no, it is not a big egg. Sorry, it is not a big egg. We got you money, but you did not get a big egg. So what we've got then is 7 cases. Now, I had 26 tests that I did on not big eggs that I said were, in fact, not big eggs based on my criteria, my technique using my criteria, my technology that I decided to use with my technique, with my criteria, and I got 26 out of 33 not big eggs right. I am done. All I got to do is run some simple numbers right here, and we are through. And you already know what they are. Let's go back and visit with them. Sensitivity tests, as you see, or expresses the percentage of subjects with the condition that tested positive for it. Now, the condition that we are testing in our experimental population is, are you a big egg or not? You either are a big egg or you are not a big egg. All right. In a clinical sense, it is the number of cases that had disease that tested positive for it, or had a disease condition that tested positive for it. Well then, sensitivity, then, break it down, is the number of cases with disease. That would be, for me, the left-hand column, as I've drawn my box, the cases with disease that tested positive for it. Oh, the ones that had the disease that I found with my test. Yes. That's it. That's my little corner pile that I've got things in. Now, if we take my experimental population right here and see what we're doing, then take a look. Sensitivity equals the percentage of time we recognized a positive condition, and that's a big egg or not, a positive condition when it was actually present. The condition was actually present 21 times. 18 out of those 21 times, I was right. Sensitivity is a measure of my ability to find that condition when it actually exists. I found that condition 18 out of 21 times. 18 divided by 21, that is to say 18 out of 21 were right. That can be related to a decimal fraction. That's 18 divided by 21 equals 0.86. Multiply that by 100%, and you've got a sensitivity of 86%. And you're all set. Your sensitivity in this case of picking out a big egg, when in fact it was a big egg, was 86%. Specificity is the other side of the coin. How good were you at picking it out when in fact it was non-existent? The percentage of subjects without the condition that tested negative for it is specificity. That is the same as clinically the number of cases without disease that tested negative for it. The ones that didn't have a big egg condition that tested negative for it. Let's take a look at our table. Specificity is the number of cases without disease, that's my right-hand column, the number of cases without disease that tested negative for it. That would be, in this case, the bottom right-hand column, wouldn't it? Now, for my egg test population right here, specificity is the percentage of time we recognized a negative condition when it was actually negative. We had a total of negative eggs, 33 in number. 33 eggs were small eggs. We found, according to our test, that 26 of those 33 eggs were not big eggs. So we got 26 right out of 33. 26 divided by 33 is the same way of saying 26 out of 33. That percentage that 26 comprised of the 33 in the whole is expressed as dividing 26 by 33. That's 0.79 is the decimal fraction. To raise that to a percentage, you'd say that's 79/100ths or 79%, or 0.79 to express 0.79 hundredths. It's really quite simple, isn't it? And you're done. Sensitivity and specificity, except wait, there's more. Because measures of sensitivity and specificity weren't enough and didn't fill up that 10 minutes people got on the podium there during the meeting, then we had to give ourselves some more numbers. I think that most realistic statisticians shy away from expressions of positive and negative predictive value. Positive predictive value, however, is the percentage of correct picks that I made. The percentage of correct predictions when a positive prediction was made. Oh, wow, that's the classic definition, the KMA definition, the paraphrase of it is, what percentage of the time were we correct when we claimed that there was a positive finding? Oh, that would be related to how many times we said there was a positive finding and how many times we were right when we said there was a positive finding. Well, that's simple. All you've got to do is figure out how many times did we say there was a positive finding. How many times in this case did we say, I'm positive, that's a big egg. It's positive, it's a big egg. Well, we said, you see by the arrow over there, that it was a big egg, that it was 25 times. Then how many times of the 25 times we opened our yap and said, oh yeah, it's a big egg, yeah, trust me, it's a big egg, how many times were we right? When we said it was a positive condition, that it was in fact a big egg, how many times were we right? I don't know. Take a look at the box. Well, let's take a look at the box. 18 out of those 25 times we were right. Positive predictive value is just then how many times we correctly made a positive prediction. We made a positive prediction 25 times. Of the 25 times we said it was positive, we were correct. That is, we agreed with the gold standard, the box. 18 of those times, 18 out of 25 times, we were correct. So 18 divided by 25 is equal to 0.72. So that's 72 hundredths. And of course, hundredths could be expressed as percentage. And we just multiply that decimal fraction by 100, and there you go. And wow, you're almost done, aren't you? Yes, you are. Only two things left. 3 things left. First of the 3 things left is negative predictive value, and that, as you've probably already figured out, is the percentage of correct predictions made when a negative prediction was made. Oh, you mean what percentage of the time were we right when we claimed a negative finding? You know, every time we said it was negative doesn't necessarily mean we were correct. Every time we said it was negative, it wasn't necessarily right. How many times when we said it was negative were we correct? In fact, negative. First, find out how many times you said it was negative. In our experimental population, we said that it was negative 29 times. Take a look at the negative egg tests, the not a big egg tests. And it doesn't make any difference whether it's running from left to right, top to bottom, diagonal, up and down, as long as you know which column, which assemblage of piles constitutes negative tests, you're all set. In this case, I just happen to draw it across the bottom because that's the way most textbooks do. You could put the slide in backwards, look at your TV through a mirror, stand on your head, lie on your side, look at it any way you want to, as long as you recognize what it is that you're doing. Out of all the negative predictions I made, how many times was I correct? Well, just take a look. I'm making a negative prediction 29 times. Okay, how many times were you correct? 26. That's pretty good. 26 correct out of 29 total picks is relatable fraction of 0.83. That is 26 divided by 29 equals 0.83. This is not rocket science. We are not going to be talking about sacraments and religion in the next frame. This is simple stuff, folks. Negative predictive value is 0.83%. How do I sound? Credible? If I say it fast enough and deep enough, then perhaps I'll sound credible enough. The closer you get to 100%, obviously, the better off you were. And we want to make sure that you did a good job in predicting positive and negative. You did a good job of picking up positive and negative patients when, in fact, they were positive or negative for any sort of disease condition that you did test. But you don't want to do that, do you? Because that might skew your results and make everybody believe that your test or your technique or your decision for use of statistical criteria was inaccurate. So in this case, I recommend just blow all that off and go to accuracy, and nobody will know what you did. Oh, I just need to know how accurate it was. No, you don't. Well, I just need to know whether it's accurate or not. Well, accuracy is nothing more than the number of corrections you made, and that can be influenced by all the different factors that you've seen so far. Population bias. You know, if I ran 100 big eggs through that study and I just said, oh, my criteria, if it's bigger than 1 centimeter in height, that's going to be a big egg. Then you'd say, wow, Keith, that ultrasound sure is good for picking out big eggs, isn't it? You begin to get the idea. Accuracy is nothing more than the percentage of correct predictions made during the entire time you were running your test period. That is to say, do you mean what was our total percent predictions of both kinds together? Did we pick out a disease when it was present? Did we exclude it when it wasn't? Did we say it was a big egg when it was a big egg? Did we say it was a little egg when it wasn't a little egg? Did they have DVT when, in fact, we said they didn't? Did they have it when we said they did? How often were we right? Well, just the number of times you were right. We don't care with accuracy whether you were right in picking up disease or normal. We just care whether you were right or not. That's the expression in percentage terms of accuracy. Now, how do we calculate that? Because as soon as we do, we're done, right? Nope, this is just the second of 3 things you got to do. And the third one is the best and most important point of all. To determine accuracy, all you got to know is, how many predictions did I make? And you tally that all up. Well, let's see. Accuracy is the percent of time we made a correct prediction of either sort, and I'd have to know the number of tests that I did and the total number that I'm going to bring in my contemporaries here. The number we predicted correctly. It's always me if my results are good, but it's my contemporary, the fact that I had to do this by committee, that when the numbers are wrong. That maybe that's why there's so many names on all these papers that we see. How many did we predict correctly? Well, out of 54 tests, we did 54 tests in total. I got 18 right in predicting big eggs, 26 right in predicting small eggs, and 18 plus 26 equals 44. So I had a total of 44 correct out of 54 attempts at testing in total. So that's 44 out of 54, which is 0.81, which is a percentage of 81%. And that's how it came out. If that's not good enough for me, I can always go in there and fudge the data later on and go steal some money out of my wife's purse and go back down to Tom Thumb Page and buy a couple of dozen big eggs and just throw them in there. I'm going to get the old extra large eggs. Remember, they're the ones with the biggest yolk that we found. The average yolk height was highest of all. I'll dump them and give me a whole lot more populations because they're going to be greater than 2.84, 2.87 centimeters high. And then I'll have a higher accuracy, and that's all I'll report in my test. Somebody asks me, well, how good are you there in your lab? I'll just say, well, I'm 99% accurate. And pause for dramatic effect. But that's not good enough for me. It's not good enough for you anymore either, is it? You want to see not only the numbers, you want to see the experiment. And that's what we do as scientists. I'm being rather flippant and playing devil's advocate here, but we've got to do that. That's most important of all. Now, we've got some eggs that are missing. We had 6 in our series that were missing. I did my best to check them at the time they left the store. Was very careful in taking them back over to the lab test facility here to run the experiment. But because I'm not Chef Mauney, that it's impossible sometimes to break an egg without corrupting the egg yolk. And I contend this was done before I got there. It is not my fault. I'm going to blame it on the trucking union. Surely they must have mishandled the eggs there and shipped. The egg yolk was corrupted by the time I got there. Now I know that egg yolk height is going to be less than my criteria for a large egg. But I have no idea what that specimen should have registered as because it's a corrupt sample. And I have to account for that. I have to say that out of 54 eggs, out of 60 eggs attempted, I had 6 cases that I could not enter into the study, and I must account for every single one of them. But I'm going to blame it on the truck driver and not on me or my handling of the data at all, am I? And the other thing is in data selection, in your patient population selection. If you're going to you better spend a little money and not just do it the cheap KMA way, going down to the store with money that we picked up from the cushions there that our clinical guests have left in their passing at various seminars. No. If you're going to test eggs, you've got to test eggs. You exclude any from the population, you are being statistically incorrect. You're not practicing good science. I ran down to Russell's gift store downstairs from the KMA Training Theater here and found, being around Easter time, you'd expect to see these, but down at Russell's you'd expect to see them about any time of the year. Cadbury cream eggs that normally only come out there at Easter. Think about that, since this study was done much later than the time frame in Easter. You're going to test a Cadbury cream egg? Well, okay, that's an egg too. Well, let's just crack that yolk and drop it into the... Oh, I see. There's nothing really to measure right there. So when you consider this, narrowing your patient population, you can't extract or extrapolate or expand the findings from one single laboratory's patient population to the world at large, because there may be other factors out there, eggs out there, that have yet to be tested under these conditions as well. Am I not right? Egg number 52 out of 54 eggs tested was a double yolker, the first one I've ever seen in my life. I've seen one other one since then, but I scrambled it and ate it. The first double yolker I ever saw was this one that you see right here on the screen. And that was just a wonder of nature to see the little twin yolks like that, but it posed somewhat of a problem for us. What are you seriously going to do with this sort of egg yolk? Are you going to measure both of them and kind of figure that the combined egg yolk height, if it was 1, would be 1.5 times that? You start getting into a prospective study where you make the rules up before you begin the study. You run into lots of roadblocks like this, and we had to throw this double yolker out. The other sort of thing is it possible that your diagnostic test could actually alter the results you're seeking to obtain? The boys sitting out here on the beach are catching the wrong kind of rays, and the beach they're sitting on doesn't have water around it for a long, long way off, because these high-ranking military officials are watching the very first above-ground nuclear detonation from a safe distance here of many miles away. But the kind of rays they're catching are of the gamma variety, aren't they? And the test that was done by the U.S. military was to subject military personnel on the ground at much closer distances to the blast to determine the effects of radiation to them. That everybody, including the photographer, and this camera's behind a lead shield, is getting dosed with X-rays that will produce effects that will stay with these boys for the rest of their life. So is it possible that in the course of your experimentation that you are actually creating some sort of alteration of the findings you hope to scientifically predict? If you do that with ultrasound, if you turn up the power too high and you're broadcasting the wrong kind of sound waves down through there for your test, then you could be cooking the tissue. Hyperthermia coagulates protein, not unlike cooking an egg. And then what are you going to do with your tissue specimen? If you test in eggs and you turn up the power too high, if that were possible for clinical ultrasound systems like this, and it was possible to produce actual tissue damage with hyperthermia, then you'd have a dickens of a time figuring out things statistically, wouldn't you? But, of course, that would be silly, because the system couldn't do it. Instead of scrambling the tissue or frying the tissue, let's just poach the tissue. What about corrupt specimens here? I've got an egg with accoutrements, pepper and a little bit of salt right there. And what am I going to do with a contaminated specimen? One in which I got some eggshell in the course of the egg. And I measure yolk height. Could that be altered by the presence of a little piece of eggshell that I didn't can't dip it out of there, might corrupt the study, Not going to do that. Got to measure it properly using meticulous technique. Oh, it wouldn't be too bad. What about incomplete specimens that you just couldn't get? Around the KMA Training Theater, you leave your data like this around too long, you come back, then what are you going to do with it then? Now, your specimen was okay, let's say, but then you come back when it's time to measure it, something else happened, or somebody's told, well, you get the idea. How are you going to account for that? Your study is already corrupted, in part, as a result of incomplete data. So we want a large number of tests, a large patient population to overcome these natural limitations that we will run into. Won't we? Well, I promised you that a third friend of mine would come into the picture right here. He's to make certain that we understand that the third thing that we've got to do with statistics is, in fact, the most important thing that we must do with statistics. And here we take a frivolous yet also simultaneously serious turn with this. And then we'll be wrapped up and you'll be dipped in the river, as we say, of statistics. The Wishnik troll is my little buddy right here. And can you detect the surface detail, the contour detail, the boundary dimensions of this little fellow right here, or this little fella, the lady, or the generic, the androgynous little character here we call the troll, here on surface imaging. High resolution ocular imaging like this, photographic and video imaging. We don't do that frequently in vascular technology, do we, or in echocardiography, the radiographic generated image of the cardiac catheterization results, and or the radiographic results from angiography, or in fact maybe perhaps CT scan or whatever would be used. And in the case of angiographic film techniques, we are, in the words of a colleague of mine, shadow boxers. Right? We're looking at shadows cast by these structures. So take a look at the shadow cast by the Wishnick troll against the background, and you'll notice that the shadow does a pretty good job of depicting what the original equipment actually looked like. And that's reasonable. We realize that medicine is not perfect, and as a tool, the angiography is in fact a very valuable one. I don't mean to besmirch that one at all. But let us continue. If you were to take a straight AP frontal plane shadow box view of the Wishnick troll, and I were to ask you, having seen the Wishnick troll, to tell me where the troll's belly button is, then, and I told you that, wait, this is a Wishnick troll, wink, 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 and that could be anywhere, then you'd probably go for, well, I guess it's probably about right, but you'd be guessing, wouldn't you? And you couldn't tell, because that particular structure was not revealed using the imaging technology that you got right here. So you'd say, well, let me try it from a different plane approach. Let me try it from a lateral plane approach here, and I'll just shoot another X-ray film here and just see what that looks like. And on angiography, you'd certainly be clinically remiss in not so doing. You want to get a better idea of what's going on inside there. If you're looking for the belly button, the navel, or the ulcer crater in an atherosclerotic lesion, you better darn sure look for it in lots of different views. And we're doing a good job of predicting what the true contour of this particular structure is. Hey, look at that hair detail. Not bad. You can't tell that it's blue, but it's looking pretty good. We're getting very, very good surface detail out of our radiographic image. And even still, I can go to an oblique view right here and even show you detail, if you look very, very closely on a good TV monitor, the detail in the fingertips of the extended fingers. But you can't really determine exactly how long the Wishnick troll's arms are in this film plane, can you? There is a limit to our so-called gold standard of angiography. And we must not proceed blindly, thinking naively that it is always accurate 100% of the time. For the first 15 years, in my experience, everybody just believed it because everybody said that that was the case. But in 20 years later, we realized that there are some feet of clay on our idols, so to speak. And we recognize the frustration and futility of trying to practice medicine as a science. That hasn't stopped us yet, though, and we get very good results when we do good statistical analysis methodology. Whoops, where did he go? Well, you need to look up at the top of the screen, ma'am, sir. And if you catch one like this, an aberrant finding from an odd or off-axis plane, that may skew your statistical findings. Here, if I was using this as my gold standard, oh, since I'm the gold standard, I can do it about any way I want to, I suppose. Or I may clinically, in fact, use multiple views there in angiography, for example, or in CT scan, for example. And the way that we correlate our gold standard to our non-invasive test or our experimental test can produce some interesting statistical challenges, so to speak. And of course, the most important frame of the entire thing is if you're considering, and I'll use as my example, atherosclerotic disease in the carotid territory, embolic disease is probably the thing that produces more symptoms, and perhaps, as we'll find out someday, actual strokes. Embolic disease is very worrisome, isn't it? We would be very interested in studying the contour of the potential embolic producing structure to determine whether or not one was present. And the angiogram may not be the ideal tool to do that because of the problems we've looked at previously. So therein lies the problem. The problem also lies in trying to decide what sort of condition to test. I'm getting more mellow here because we're getting more serious, so I'll shift gears just a little bit and look at you eye to eye right now. In Da Vinci's text, his own sketchbook text, paper was not cheap then, and though he was well funded there by the patrons of the arts and the sciences there back in the 1500s, as I recall, he spent a lot of his time, actually spent all of his time, involved in various pursuits in enhancing the mind. Science was one of them. And he was one of the first to begin to describe, in more contemporary times, the nature of turbulence. And you can see there that he would take his book, a book which is not cheap at all, hold that into the water along its short edge, and describe on paper. He could scientifically then at that point describe the nature of the flow characteristics around it. and then turning the book to a slightly wider angle in separate diagrams, he would show that sort of effect, and would study the water, the flow of water in multiple conditions in many different rivers and streams and sites, high flow, low flow, and this sort of thing. And you can see then that to scientifically describe this sort of chaotic pattern, of which turbulence is a perfect example, just on the surface, it becomes extremely complex. Yet over the years, of course, turbulence in the early years, the first 20 years of non-invasive vascular technology, was purported to be a rather straightforward, easy to assess thing. We put some hard and fast numbers on it that said that if the bandwidth was greater than this or greater than that, then using our standardized terminology and techniques, that this would constitute disease. And if it wasn't that, then it wouldn't constitute disease. But there were many other variables to play into that had to be investigated as well. And though I'll not take a position in public on the benefits or the detriments of detecting turbulence as a standalone criterion, it has shown in any series to be really sort of random by itself. It is a very helpful sort of tool and merits more scientific investigation. You know, if nothing else, it ought to help us predict what sorts of numbers will come up on dice in the casino someday. If someone claims that they've figured out a mathematical equation to predict with precision turbulence, then I would think surely they're not much far away from breaking the bank in Atlantic City or in Las Vegas. So what are you still doing here, sir or ma'am? I'd like to see your experiment, not your data. Oh no, I'd like to experiment. I really would. So with that, we must take statistics a little more carefully. Johann Blumenbach was the father of modern anthropology. Cranial anthropology, as it's known. He was the first to actually categorize the human race into 5 separate families. He divided these skulls up into piles based on measurements of cranial size, cranial volume or capacity, and simply described statistically his findings and said that skulls which were found over years unearthed from the North American continent seemed to belong to a certain family of people. Their skulls were all this wide and this tall and had a certain volume, brain volume capacity of this big. Certain aboriginal skulls in the other areas of the world, for example, would have a larger skull capacity, larger brain content capacity. Their skulls might be wider or longer front to back. There was a mongoloid family of humans that he classified there. Again, all he's doing is putting labels on piles. I talked about an egg-sperimental population. He's talking about simply classifying his findings that he's discovered in his lifetime based on statistical analysis of skulls. And he came up with some other subclassifications. And his last name is Blumenbach, B-L-U-M-E-N-B-A-C-H. And you can read more about him in any encyclopedia or library. And when you do this more carefully, you will be horrified to find that a student of this anatomy professor and father of anthropology was very taken with this work. And he took these statistical findings to heart. And he began to add to this his own political aspirations and his peculiar, nutty bent of mind. And Adolf Hitler began to develop his own burning desire to purge the world of these other families of human beings that had inferior skull sizes and thus inferior capacity and were inferior as human beings and did not deserve to live. And fueled in his formative years this sort of burning, nutty philosophy that unfortunately was taken to the front of World War II and was fortunately defeated, but fueled in part, unwittingly, by the careful scientific and innocent work of Dr. Blumenbach early on. It is possible to take statistics much too seriously and to believe too strongly in your very own work. Please don't take it to those nutty extremes that lead to massive death and annihilation such as the world has seen before with statistics. And before you jump to the microphone there in a scientific meeting and begin to debate the scientific accuracy of that particular study, why don't you corral that person and say, excuse me, you know, I may be wrong, but I think you may be wrong, and let's discuss it further over a cup of coffee and I'm buying. Let me take a look at your experiment, if I may, and see if, in fact, I might be able to duplicate those same findings. Life is way too short. In the words of Oliver Cromwell, who led England through one of his ages there, in fact, the middle and dark ages of England, wherein science did not flourish, one of the most valid comments in statistics and science ever came out, quote, "I beseech thee, in the bowels of Christ, think it possible you might be mistaken." Always take your statistical results with about the same degree of seriousness that we have presented our experimental population to you here today. Always test your experimental results. Have a good time when you emerge from the drawing room with your data in hand and a big grin on your face. That you will certainly have joined the large worldwide and historical human community in trying to describe the world in numbers. And then put the numbers there in a folder. Go put an egg on the skillet, cook it up, and enjoy it, and think about us when you do. Ladies and gentlemen, it's been our pleasure to bring to you KMA's version of statistical analysis.
If you have any questions, contributions, want to bless us out over the phone or laugh with us about your findings, then please do give us a call. Our office numbers are open 24 hours a day, every day of the week, every day of the year. You see, we have no life. No, we'll be staffed with live operators that can relay emergency questions and the like to us. It's our privilege to share with you what we find there in the scientific community, what we can in the way that we do. So any input and insight that you have, please share with us. Our phone number is there on the videotape box, and the tape cassette itself will be waiting to hear from you. Have at it and enjoy it. Thanks for listening. Bye-bye.